We now work with this extension here where y is a function of x1, x2, and w, and x1 is a function of w, and x2 is a function of w. So what we have here is w affecting y through three channels. First of all, directly, as we can see through this f function, indirectly through g, and another indirect channel through this function h, where w affects x2, and then that affects y. So we've illustrated that here, also using a channel map and illustrating these three channels. The two indirect channels via h, w affects y via h, affects x2, and then affects y through f. x2 affects y through f. The second indirect channel, where w via this function g affects x1, which then impacts on y. And then lastly, the direct channel, where w impacts on y. So we want to find the total derivative, and our approach is the same. We start by setting out the differential, total differential dy equals partial here, okay, times dx1, this partial derivative here, times dx2, plus this partial derivative here, times dw. Okay, and the next step is to then divide both sides by the relevant differential. And in this case, it's going to be dividing through by dw, because as we said, w is what's impacting on y. So we divide through by dw, and here we have the total derivative of y with respect to w, and dividing each of these terms now by dw, we end up with this indirect effect, which is showing how w indirectly affects y through x1. The second indirect effect, where w affects y through x2. And then lastly, the direct effect of w on y. And remember, this dw over dw will cancel to 1. We now work with an economic application where we have this production function, Q, which is a function of capital, labor, and technology. And then we also have capital is a function of technology, and labor is a function of technology. So technology is ultimately responsible for changes in Q. So if we want to calculate the total derivative dq over dt, our starting point is setting out the total differential dq. We have the partial derivative of q with respect to k times by dk plus partial derivative of q with respect to l times dl plus partial derivative of q with respect to t times dt. Now we need to divide through by the relevant differential, which, as we know in this case, is technology. And that's what we do on the next line, dq over dt. And we also need to divide through by dt on the right-hand side. So we have this term here, and this is the indirect effect of technology on output via capital, the indirect effect of technology on output via labor, and the direct effect of technology on output. And recall, when you divide here by dt, that will cancel to 1. So we would have a 1 here. And this last line here sets this total derivative out, just using slightly different notation to indicate the partial derivatives. And there. And here we have y is a function of x1, x2, u, and w. And the difference in this example now is we can see x1 is a function of both u and w, and x2 is a function of u and w. So the ultimate source of change in y comes from two sources, u and w. They both act on y directly and indirectly. Okay, through this function g, both w and u are working indirectly on y by affecting x1, and then x1 affects y, and similarly u and w act via function h, affecting x2, and then acting on y. So I'm going to leave it to you to illustrate these effects, the direct and indirect effects, using a flow diagram, or we can refer to it as a channel map, as you saw in the previous examples. And we're going to go ahead and work out total derivatives. So we're going to start by setting out our total differential dy. So that's the exact same approach that we've been using up until now. Starting with the partial derivative of y with respect to x1 times dx1 plus partial derivative of y with respect to x2 times dx2 plus partial derivative of y with respect to w times dw plus partial derivative of y with respect to u times du. Okay, so we have now set out the total differential dy for this function here. And we're going to start by varying w. Okay, so we're going to allow w to vary, but we're going to hold u constant. Okay, so the relevant differential in that case that we need to divide both the left-hand side and the right-hand side by is dw, because that's what we're looking at here. So if we do so, we end up with dy over dw, and dividing through by dw on the right-hand side, we end up with this here. So if we take what we had on the previous slide and just set it out here so that we can continue working with it, there's a couple of things that we have to do now. For starters, this here, dx1 over dw, this needs to be written with a partial sign, because to calculate this, we are going to be working with this function here. And recall that we are currently holding u constant as we allow w to change. So as soon as we do that, we are working out a partial derivative. So this here would be the partial derivative of x1 with respect to w whilst we hold u constant. Similarly, if we look here, we have to replace this d also with the partial derivative sign, with the curly d, okay? Because if we look at x2, x2 is a function of u and w, and we are holding u constant and allowing w to change. So this here should be the partial derivative of x2 with respect to w. So if we see on the next line down, that's exactly what we've done. Instead of using the d, which would indicate total derivative, we need to use the curly d to indicate that it's a partial. And similarly here, we wouldn't have this notation, we would use this notation here. All right, so this is on the right-hand side, but also on the left-hand side. Because we are allowing w to change and keeping u constant, we really need to interpret this as a partial derivative, even though it is being derived through the process of the total differentiation of y. Okay, so we can't think of this now as the total derivative where we allow everything to change, okay, because we are holding u constant. So in order to indicate that, we will use this notation here, and our expression we now can refer to as a partial total derivative. Okay, so that differs from the examples that we've been working up until now, where we have been finding the total derivative. We now have the partial total derivative because we are holding, in this example now, u constant. All right, and if we have a look here now, let's just go back to this line here. Recall dw over dw, that will equal 1. So in effect, you will have 1 here. And for this last term here, all right, we are holding u constant. We are not allowing it to change. And in any event, this last term here would be 0. This part of the last term here would be 0. Okay, so this would all be 0. So stating what we worked through on the previous slide more formally, du over dw is naught, as we said. There is no explicit relationship between u and w, and these are assumed to be independent. Okay, so in other words, when w changes, we aren't going to see a change in u. All right, so we can hold u constant when we allow w to vary, okay? And as we said on the previous slide, when we do so, we have to re-express these derivatives using our partial notation, and we have to treat them as a partial, okay, because we saw that x1 is a function of both u and w, so we are partially differentiating with respect to w and holding u constant, and similarly with x2. Okay, so as we said, our expression changes to a partial total derivative. So we cannot work out the total derivative because we are holding u constant and we are not allowing all the variables to change at the same time, which would be the case when we calculate a total derivative. And also just to point out that, remember, we cannot find the partial derivative as we did in topic 5, because when we calculate a partial derivative, we have to assume that the independent variables are not related, and in this example, they clearly are. Okay, u and w, well, rather x1 and x2 are a function of u and w. Okay, so this example, we are calculating a partial total derivative. The last thing we need to do is, working with the same example, we now need to allow u to vary, holding w constant. Our starting point is the same as when we allowed w to vary and held u constant. We need to find the total differential dy, and that's what we have here. And the next step is then to divide through by the relevant differential, which will now be du. Okay, so we would divide the left-hand side and the right-hand side by du, and the final expression would look like this. Remember, dy over du, right? We can no longer indicate that it's a total derivative because we are holding w constant. So we have to use this notation here, and this indicates we are finding the partial total derivative. And then on the right-hand side, we will have dx1 over du, and that too needs to be indicated as a partial derivative because x1 is a function of both u and w, and we would be partially differentiating x1 with respect to u, holding w constant. So we need to use the curly d's to indicate that this is a partial derivative. And the same for dx2 over du. That would also be a partial derivative. Okay. For this term here, when we divided dw by du, that would be equal to 0, because as we've said, there is no relationship between w and u. So this would equal 0. So this whole term here would equal 0. And lastly, dividing du by du would give us 1. And that's what we would have here. Okay, so here we have our final expression, which is a partial total derivative, where we are calculating the change in y, allowing u to change, and holding w constant.